The objective of this course is to learn how to solve partial differential equations. In order to find the solution of partial differential equations, we need to learn Fourier analysis, which is the focus of chapter 11. The reason we need to learn Fourier analysis is because the solution of a PDE usually involve Fourier series. And in this chapter, we are going to learn how to represent a given function f by Fourier series. And this f usually has a finite range of interest. If f has a special property, for example, if it's even, odd, or half-range functions, then our computational techniques can be significantly reduced. That is why we need to learn how to reduce the effort. In the second half of this chapter, we're going to learn Sturm-Liouville problem. This type of problem is also called boundary value problems or eigenvalue eigenfunction problems. We're going to demonstrate that the Legendre and the Bessel equations we learned earlier are all special cases of Sturm-Liouville problems. One of the major reasons we want to learn Sturm-Liouville problem is because its solution involves eigenvalue and eigenfunctions. And the eigenfunctions have orthogonality, which is very important in solving PDEs. Finally, at the end of this chapter, we're going to discuss Fourier integral representation of a given function which has the range of interest in x extended to infinity. First, let's talk about Fourier series. And we have to learn what is a periodic function. The shape of the periodic function repeats itself with period equals p. Mathematically speaking, we can represent a periodic function with period p in this way: f evaluated at x plus p equal to f at x. And on this slide, we show two special properties of periodic function. And then we are going to start the discussion of a group of functions. First, if f has a period p, then we can state that f at x plus np equals f at x, where n is any positive integer. This can be understood because the function repeats itself. And the second, if f and g are two functions, both have period p, then any linear combination of these two functions will have period p, where this a and b are arbitrary given constants. In the third part, we have a special collection of functions involving element 1 cosine x, sine x, cosine 2x, sine 2x, etc. And in a more compact way of presenting this group of functions is like what I present here at the bottom. If every element in this group has a period 2 pi, then according to what we state here, linear combination of all of them will have period 2 pi. That's what I show you right here. Any linear combination of this element can have period 2 pi. Now, let's discuss a topic which is closer to our purpose to finding the solution of PDE. We will need this skill if we are given a function f with a period 2 pi. Then we have to represent it by a Fourier series, where our immediate job is to find these 3 groups of constants. And in order to find these 3 groups of coefficients, we have to know we can derive this group of equations at the bottom of this slide. This group of coefficients are called Fourier coefficient, and this representation is called Fourier representation of f. In order to prove these 3 formulas, we have to know the so-called orthogonality of this group of functions. Orthogonality can be qualitatively stated in 2 parts. First, integral of product of any 2 different functions in the set is 0. Integral or product of any 2 identical functions in the set is non-zero. So that is stated mathematically in these 3 equations. If the elements are different, element in this group of functions, notice sine nx and sine mx are 2 different elements in the group. And sine nx, cosine mx are also 2 different elements in the group. They all get 0. If we use this orthogonality, we can easily derive this group of coefficients, taking an as an example. In order to get an, we multiply this equation by cosine nx, and then integrate both sides by from minus pi to pi. As we already explained, integral of 1 and the cosine in this range will be 0. Integral of sine times cosine will be 0 too. and integrating cosine nx with a different element will be 0 too. So this summation index will reduce to only one element. That's two identical cosine functions. That's how we get an equal to what we present here. They are proved in the textbook. So in order to get Fourier series representation of a given function f, we have to use these three formulas to get the Fourier coefficients, which is our immediate job. And before we demonstrate we can get the Fourier coefficient, we have to discuss under what conditions the Fourier representation exists. The condition is not really very stringent. As long as the given function f is piecewise continuous, then we can represent the function by Fourier series. Now, let's look at this example. If we are given a function like this, either negative k or positive k, and it repeats itself with period 2 pi, then we can sketch it very easily. And here I remind you that the required scale for this chapter is how to represent a mathematical equation to graph, and how to represent a sketch to equations. If we want to represent this piecewise continuous function by Fourier series, we need to get these three groups of coefficient, Fourier coefficient. We can already tell A naught is 0. The reason is we have integrating f from minus pi to 0, we get a negative area. Integrating f from 0 to pi, we get a finite area. And this negative area have a identical area with different signs. They cancel out. So A naught, according to the formula we discussed, integrating f, A naught has to be 0. And to get An, we use the given formula. And because f is piecewise continuous within this range, we have to break the integral into two integrals. One involves integrating this product from negative pi to 0. The second part, we integrate the product from 0 to pi. And eventually got 0. And to get a Bn, we use this formula. We break it, the integral range into two parts, like we get An, and we get this expression after we substitute the lower integration and the upper integration limits, we get this expression. Then here we notice, because cosine n pi can be either 1 or negative 1, depending on the nature of n. If n is even, we get a positive 1. If n is negative, is odd, then we have a negative 1. Therefore, this result, this factor become either 2 or 0. Substituting this result in this term and put Bn, Bn can be obtained in the following way. And then the Fourier series representation can be expressed in this way. And then we can look at the one-term sum. That means S1 is simply the first term. Two-term sum is designated by S sub 2 is the summation of the first two terms, etc. And then the graphic representation of one-term sum comparing with the given function is shown in the first graph. You can tell the blue curve is the Fourier series representation of the given step change functions. And then if we take two-term sum, the result is slightly better than one-term sum. And if we take three-term sum and compare with two-term sum, we can tell the result is further improved. We also notice all the blue curves, the partial sums, one-term sum, two-term sum, and the three-term sum pass through the origin. So based on what we discussed on this schematic representation, we can make two important conclusions. Number one, when we include more terms in the representation, the result is more accurate, closer to the given function. Number two, at the discontinuous point, the partial sum always give us an averaged value between the two points. Always give an average. That means the partial sum always take the middle ground at the discontinuous point. And another interesting result is if we replace the x by pi over 2 in the sum, we get this interesting result. At a discontinuous point, we know the function value is 0. So if we put it is k, sorry, is k at a pi over 2. At a pi over 2, function value is pi is k. So function value is k at x equals pi over 2. Then using the series representation, we get this interesting result. And this result is actually called Leibniz formula. Very interesting result. Next, in section 11.2, we are going to do 3 tasks. Number 1, we are first going to extend what we have, the period from 2 pi to more general case, 2L. And then we discuss 2 special cases, even, odd, and the special and the half-range functions. When we extend the period from 2 pi to 2L, the Fourier series representation can be represented in this way. The correct Fourier functions can be written in this way. And if for this general expression, the Fourier coefficients, these three groups of three Fourier coefficients will be our next immediate jobs. And again, they can be obtained by the orthogonality, as stated before. It's same, essentially same as those representation with period 2 pi. The textbook has deviations. If we want to take a special case as an example, if we want to get the B sub n, we multiply this equation by sine n pi x over L to both sides and integrate the resultant expression from negative L to L. Most of the terms cancel out, except when we multiply for the term we multiply by sine n pi x over L, we get two identical terms. That's how we get a Bn. Two other coefficients can be obtained in a similar way. And our immediate job is how to obtain those Fourier coefficients based on these formulas. And before we discuss examples, we discuss what are even and odd functions. If f is an even function, it has this property. In mathematical expression, f evaluated minus x equal to f evaluated x. And graphically speaking, f is symmetric with respect to the y-axis. The function on the right and the function on the left of y-axis are like mirror images. In this case, the integration for the Fourier coefficient can be simplified, and that the result can be expressed in this way. Only A0 and An remain as non-zero terms, and the Bn is 0. And also notice the integration limit is no longer negative L to L. It's from 0 to L because the area on both sides of this expression are identical. Why is Bn equal to 0 for an even function of f can be discussed from we can look at from this expression. If f is even, we know sine is a odd function. Product of a even and odd function is an odd function. If we integrate an odd function, we get 0. That's how we can say Bn equal to 0. Okay. For an odd function, we have this property. F evaluated minus x equal to negative f of x. In its sketch, it's like this. And we can say it's symmetric with respect to the origin. That means if we have a point, let it pass through the origin, draw a straight line, we get a point which is right on the function, the given function. And for this case, A num and An are all zeros. And the integration limit also change from 0 to L. Why is An be 0? We look at the last slide. If f is odd, we know cosine function is an even function. A product of an odd and an even function is an odd function. So the integration is 0, and the An is 0. If f is odd, integrating f from negative L to L, as we said earlier, is 0. So this is the best scenario. If we have an odd function f, then we don't have to integrate A naught and A sub n. They are 0. We immediately write 0. And we only need to integrate B sub n. So our computational effort significantly reduces. Now we are ready to see some examples. In this example, we have a sketch, and we can convert this sketch to this representation. It's a piecewise continuous with a period equal to 2L equal to 4. That means from -2 to 2, it's a periodic. Then we can use what we just learned. Once we look at this function, we know it's an even function. For an even function we discussed earlier, we have to take A naught and An. So this is what we can do. Put in the function value, and we don't have to integrate the range where f is 0, so the integration effort becomes a integration of a narrow range function. Then we can tell for this result, An can have different signs depending on the value of n. So we have to discuss the result in 2 different parts. And B naught is 0, we discussed earlier, because this is an even function. Then we represent the given function in this Fourier series representation. The next example has this kind of sketch. we shall be able to represent in this mathematical way if, again, the period is 4, then we notice this is an odd function. Then we only need to know b sub n. We only have to take the integrals for b sub n. Once we integrate this, we found the Fourier series can be represented in this way. Also, if f is a special type of function called half-range function, it can simplify our effort in getting the Fourier coefficients. If we have a sketch like this, we can write this function in this form. How do we get it? We break into 2 pieces. For the first part, because we know it passed through the origins, and at this point, we know the coordinate, we can generate this. Similarly, for the second segment, we know the coordinates of this point and this point. We should be able to generate this. But I urge you to practice. Make sure you can derive this equation. Alternatively, I urge you to know how to represent this in a graph like this. It's a 2-way street. You have to know how to do both. If we know the period is 2L, then we do not know what happened to the other side. We don't know how it repeats itself. So this type of function is called half-range function. That also means we have special interest in the function value in this range from 0 to L. So the other side, we can represent either as an even function or an odd function. And this type of integral will take some effort because when we put this in the Fourier series representation, the integral will be difficult, but it's manageable. Finally, at the end of this segment, I'd like to make a comment. It's too bad we have a virus spread, so most of you probably will not have access to MathCAD. If you have MathCAD, you can let MathCAD to integrate this for you once you create a template. I will devote my next segment to a few examples. I have illustrated them in the study guide.